Hello, today we are going to learn about robot localization and one of the most famous techniques, that is the Kalman filter. In mobile robotics, it is essential to know the location of the robot. Needs to know where it is in the environment in order to move around it, right? If the robot needs to pick up objects, it needs to know its location and the location of the objects. If it needs to deliver um, objects, it needs to know the location where it has to go. So this is an essential problem that we have here. Let's imagine, or let me give you a context. We have, in this context, we have a drone or a mobile robot in a planar environment, but the robot doesn't know where it is. It can try to identify its location, and that's what we are going to study in this video. In order to obtain its localization, the robot can use its sensors. What kind of sensors it can use? It can use cameras, it can use global positioning systems, or internal sensors like accelerometers. In general, accelerometers and gyroscopes, even compass, there are many internal sensors that the robot can use. In this context, the main question is like, how can we use these sensors to identify the location? Even the GPS is inaccurate. Right? The GPS can give an error of around 3 meters. If we talk about a self-driving car, 3 meters will be the difference between being inside the road or outside the road, so that's a critical situation. In this context, we are going to assume that we have some landmarks. Let's see that we have some trees in the environment, just to help the robot to identify where it is. And those landmarks will be part of the map. Now, in the case, for example, of the camera has a range. So that's what we call the sensor footprint. And this is our drone. The first part that we will use here is about predicting the location, or how to use odometry in order to obtain to estimate where the robot is. Let me give you another example that is pretty simple. Let's assume that we have a planar environment here, and let's do a simple exercise. There is a human, and the human has the eyes covered. You can imagine that you are that human. And now, what happens if the human gives 3 steps? You kind of can guess where you are going to be, maybe here, but maybe here, or maybe here, maybe here, maybe here, right? That happens because the length of our steps are not perfectly synchronized or aligned. Like we don't have an accurate measure of the length of the step. So there is an error involved there. If we have more steps, let's say that we walk for 10 steps, then the error will be higher, right? We can be here, here, here. These are all the places where we can be. And we can assume, or we can try to start to model that that type of error. Like our error will be inside this ellipse, and if it goes farther, it will be inside this ellipse. So this is just basically counting steps. In robots, we can use something similar using odometry. Using odometry, we can use something like if this is the state of the robot, with the x and y coordinates, and we know the speed of the robot, we can integrate the speed to obtain the new location of the robot. So the goal of using this prediction is basically estimating a new location based on the control input. In mobile robots, we have something similar as counting steps that is based on odometry. For example, if we have a differential wheel drive robot, this robot will move forward. If the control input is move forward, if the robot is perfect, it will fall here. If the wheels spin a little bit slower, they will kind of fall around here. But if one of the wheels is faster than the other, it will kind of fall here, fall here. If the error is very big, it will be like this, right? And same for the other side. This is called the banana shape error. In a quadrotor, and similar to the model that we will study today, will be something like this. We have the drone, it moves forward, and we can assume that it will try to fall here, but sometimes it has some error falling from error braking, and this will be kind of the distribution that we have. It will be a normal distribution. So in this case, what we have is we want to know the probability distribution of x given the previous time step and the control input t. Okay, so here we have that x is equals to xy, and x dot is our control input. Based on this model, and if we assume that the model is linear and very simplified for holonomic robots, we will have this equation over here, where the new step is equals to the previous step plus the integration of the control input, which is the velocity during this time interval, plus the error, right? And we will assume that that error is just a normal function. We will go in details later in this video. The main problem of the odometry is that the error will be accumulating while we move. For example, if we start in this location, we apply the following control inputs, what we are going to see in the end is that the error here, for example, for the drone, the error is very small in the y-axis, but when it breaks, the error can be higher. So after the movement, the robot can be here, or it can be here, or it can be here, or it can be here. Right now we have a range where the robot can be. If we apply, if we move again, we will have an error around this ellipse. because if the robot was in this location, if it moves, now it will be here or maybe here. And if we combine all of them, we will have something like this. When we apply the next control input, we will go, our error will grow like this, and for the last control input, our error will be like this, very big. And if we continue, we'll continue growing and growing and accumulating. This is the clean representation of our ellipses and how it will be if we continue using the odometry. We know that the odometry is not enough if we want to have a good estimation of the localization. So we can use additional information, like we can use the map, and we can use additional sensors like cameras or GPS. And now let's come back to our scenario where we have an environment, and inside the environment we have some trees that are part of the map, right? Or they are landmarks. So if our aerial vehicle can see one of those landmarks, it will have a better estimation of where it is. Or if it uses the GPS, it will have an estimate and a better estimation about where it is. So one way to model this in a very simple way and could be that the measurement that we get is equals to the real value of the robot plus an error that we will denote as lambda t, and we can assume that that error is normal. It's normal with meaning 0, and we will have a covariance matrix. Okay, so this is basically to identify that's basically the perception model of the robot. Now we will find a way to combine those two type of measurements that we can get from odometry and from the perception model. So what we have, this is a hidden Markov model, and this is the Markov models principally study base networks that change with time. So we have the state of the robot at time step 1, and it evolves to time step 2, and so on. It continues evolving with the number of time steps, right? The problem is, like, we don't know this is hidden. That's what is called the hidden Markov model, because we don't know that state. This is just the base net representation of the hidden Markov model. It's a graph where the nodes are variables and they have a distribution, and they evolve with time, and the variables, or in this case the state of the robot, is the states at every time step are independent. That's one of the assumptions of the hidden Markov model, and that's the same for the measurements. So we will have some measurements for every time step. We have measurements, and actually this is we have access to this variable. The only problem is, like, this variable has some error. And additionally, we have also control inputs, and the control inputs can only influence the current time step. They cannot influence, like, the future of the past. Okay, so we have U1, U2, U3, and for every step we have a control action, and we can also have a measurement of the state. Okay, so what we want to obtain, or what we have now to obtain, that is the probability of xt based on the state in the previous step and the control input, right? So what if we combine these two values to obtain this value over here? That's the first part. And the second part that we can obtain is the probability of xt given zt, which is here basically this part over here. Based on the measurements, we can also estimate the variable. And a specific model of the hidden Markov models is the Kalman filter, which is within the family of the Bayes filters, mainly because they use the Bayes theorem to estimate the hidden variable based on the evidence. The Kalman filter has been very important in robotics and in many sciences. Just to give a fact, the spacecraft that went to the moon for the first time, when the first man put a step on the moon, was based on the Kalman filter. We will see that its computation is very simple, and they were able to implement that in the computational power that they have in the moment, which basically what we have in a simple calculator these days. The assumptions of the Kalman filter are basically that all measurements, estimations, motion, all the beliefs of the state are Gaussian distributions. So let's start with the initial belief. Initial belief of xt, which is a normal distribution with a center in the location that we think that where the robot is, and covariance that's associated with the error or our estimation of where the robot is. So if we want to see it graphically, this is kind of the coordinate system. Our robot is here, or that's where we think that the robot is, but we are not sure at all. So maybe the robot is around the circle, or if we have a pretty good estimation, we can say that it is around this ellipse, and the ellipse is associated with the covariant matrix. So the first step is the prediction step. It's the prediction based on motion, like when we walk some steps and we try to estimate where we are based on the number of steps that we counted. So for that, we use the control input and the previous step, right? And this prediction is based on a normal distribution that will model the motion, and we will have mu t. Let me write down. This is the mean that we put a bar just to say that it is based on the prediction, and we have a covariance that is also based on the motion model. Our next step is the correction. We walk some steps and now we need to correct them. We correct them based on the measurement that we obtain. Okay, and the result of this correction we will be also a normal distribution with estimated mean and covariance, right? This is the output. The output will be the normal distribution, and if we continue doing this process, we will have a good estimation of the robot. So the first step will be having the robot with an estimation of where the robot is. We apply a control input, and the control input will guide us about where the robot can be, but the error might be, actually the error is bigger than in the beginning. At least the good part of this is that we know that we are around this area, but for example we will not be behind. This is wrong. This is not. We will be inside that area. Okay, and in the next step what we do is to combine our previous estimation of where the robot is and the estimation of the that comes from the measurement, and we will combine the to improve our estimation of the robot. So as I said, the Kalman filter is based on Gaussian distributions. Everything is a Gaussian distribution. We have that t-1, we have that xt, we have zt, and even the model of the motion will give us a Gaussian distribution. When we operate with the Gaussian distributions, we multiply them, we add them, and the result is also a Gaussian distribution. That's a nice property. They are close. So we have another assumption. The other assumption is that our system is linear. So we will call it a linear stochastic model. And I will write down the general equation for, or what we assume in the Kalman filter, which is that the new state is equals to a matrix that relates the previous state and the new state, plus a matrix that relates the control input and the state, and finally an error, which is a normal distribution. This error follows a normal distribution. Okay, and we have a measurement. Which is basically the variable z that relates a matrix that relates the inputs, or not the inputs, the state, and what we can see from the state, plus an error. Okay, this is the general Kalman filter. In our case, we will simplify this, and we will just assume that the control input is the velocity, so we just need to multiply this by delta t, and we will obtain the desired state, and a, the same variables of the previous state are the variables of the new state, so this is the identity matrix, and we will keep this the error the way it is. For the output, we will assume that we can see all the variables of the state, so we will have I. So we will have, in this case, we will study like a simplified Kalman filter specifically for holonomic robots. If we, the important part is like, if we know the state that is x and y, and we can control its velocity. If we have this type of model, we can apply multiple simplifications in the Kalman filter. So as a result, what we will have is that our motion model we will represent it by the mean of a Gaussian. This is a Gaussian with mean equals to the mean plus the control input. Here there is a delta t that we can assume that is 1, and we need for the Gaussian distribution of the normal distribution, we need covariance. So the covariance will be equals to the covariance that we had plus the covariance that we had because we were moving. So that's the covariance of the prediction. And second, we will have the measurement model. Right, this is the second step of the Kalman filter, where we do the correction. The important part here, and this is what they call the Kalman gain, which the equation is equals to the covariance that we obtain from the motion model times the inverse of adding the covariance that we had from the motion model plus the covariance of the measurement. Okay, when every time we read, we try to identify the location using a sensor, we will have an error associated, and we abstract that with the covariance matrix that is here. And we will use this Kalman gain to obtain the normal distribution of that represents the location of the robot. The good part, since we see like here we are adding and here we are multiplying. The difference is like when you add two normal distributions, they will start to spread, so the error grows. But when you multiply, and that's what the gain, this is called the Kalman gain, is because the error will be reduced, or the estimation will be reduced, because you are combining two different types of estimations. Okay, so our result will be the mean at time t will be equals to the mean of the previous normal distribution that comes from the motion model plus the Kalman filter, the Kalman gain, that relates the measurement and the previous estimation. Okay. Now the covariance will be equals to I minus kt, and this is kt. We can see that these equations are in the book, and the derivation of these equations are pretty interesting. Today we are going to focus on the intuition on how they work, and later we can study the derivations on how to obtain those equations based on the estimations, the prediction model, and the combination of them. So now, before the Kalman filter, what we had was an error that was accumulating. So let's see that we start here and we move in this way, then we move in this way, then this way, finally this way, right? and we had that the error was accumulating. Just to give an example, we can have the real robot. The real robot was very close to our estimation, but when we move forward, it moved to here, it moved to here, because it doesn't even follow perfectly because there is an error in the control input, and it moved to here, and finally the robot will be here. If we see what we can see from the measurements, the output that we get from the measurements will be something like this. This is after the simulation. We can have this, and it says that the error will be around this. The second measurement will be here, third measurement will be here, and the fourth measurement will be this. If we use the odometry, the error is pretty big, but the real robot is still inside the range, or the 90% of the area that is covered from the Gaussian distribution. Now, the problem is with the measurements. Like, the measurements don't change with time, they are kind of constant, but they are still big all at every time step. So now we will see what happens if we use the Kalman filter. Now let's apply the Kalman filter to combine the information that we have. For that, we will start saying that our robot is in this location. It will apply a control input that goes in this way, and since there is an error associated with the motion, it will fall in this point. Now it will apply a control input here, and it will fall here, and we will repeat that process, always taking into account that there is an error in the motion. So this is what happened in reality. And the final location of the robot is here. Okay, so from the first odometry, from the odometry, what we get is that we will be around this location. Okay, and our measurement will be this here. Okay, so this is pretty bad, and we had a very small error based on the initial localization, and now it grows. If we continue, we will have that the localization error grows here, and the estimation will be around here. The error will be, this will be the error, and if we apply the Kalman filter, what we will obtain is that the estimation, our estimation will give a location around this area, and that's based on the covariance matrix. Now we see that the error is way smaller than the initial error of the GPS, and now we combine the motion of the odometry with the measurement of the GPS to improve our estimation. Okay, it doesn't have to be the odometry, only the odometry, the GPS. It can be like we detect landmarks, and it helps us with the estimation. If we continue using the Kalman filter, we will obtain something like this, and finally something around here. This is a pretty small error in comparison to the first initial estimation that we had about odometry, and the final and the measurement from the GPS that is always constant. This will be a clean version of what we will have if we combine them all the time. If we have a case where our initial estimation is really bad, like we have no idea about where we are in the environment, we can make the initial covariance matrix very big, such that the error will be huge. We can place them in everywhere, and then we will make the covariance matrix very big. Okay, so we can say that this is the real robot and our initial estimation is there, but we have no idea where it is. Based on, if we run the simulation, we will obtain that the estimation will be getting smaller and smaller and smaller every time we run the Kalman filter and we combine the information from the odometry and the information from the measurements. And in the end, we can see that this estimation is significantly smaller than the initial that we had. In comparison, we have that without the Kalman filter, the errors are growing if we use odometry, and if we only use the measurements, they are still big. But if we combine them, we will obtain a smaller estimation that grows, that keeps being smaller all the time. For the implementation, we can start creating a robot simulation, and this robot is pretty simple. We just give an initial location when we create it, and that will be the state of the robot X. We know that the sensor has some errors, so the covariance of the sensor will be given in the initialization, the same as the motion. So when the robot moves, it will compute the covariance matrix depending on the initial motion covariance. Like if the robot moves here, it will move like this, but if it moves longer, that covariance should grow. Okay, so it will be proportional to the distance, and also proportional to the error in X and Y and the direction of the control input. And the output will be the output will be xt will be equals to xt minus 1 plus delta t u. We assume that this is 1 plus the error, and the error is given by this. So every time the robot moves, it will involve that it will have an error. And for the sensing, we have a sensor that just gives the value of the actual state of the robot plus the error. This is the error that we used to call delta t. So it will be z equals to ct equals to xt plus the error. And this is the way we write we obtain a Gaussian error. This is a pretty simple probabilistic robot that moves with an error, and it also gives the location with an error. So now the implementation of the Kalman filter is pretty simple actually. What we have is that we create our simulated robot. We don't know how that robot moves or what it gives us, but we have the model of its error. That's something that we have to be aware here. Is our predictions will depend on how good how good our models are, how close they are to the reality. Okay, so we will use the same constants, and here when we have the control inputs is where we are going to start moving around. And now this is our initial belief of the robot that is very accurate, and then the robot will start to move. So for every time step, for every control action, our robot will move. And now based on that motion we will have our prediction that uses the time of the previous step and the control input. This is the control input that we obtain over here, and we said that the error will accumulate, it will add from each control input to the next one. Now we obtain the measurement and we apply the Kalman gain, and we obtain the estimation based on the measurement and the Kalman filter. Using this method multiple times, we will obtain that our current estimation is very close to the real one. This is just an example. After running this code, we will obtain something like this. This is the actual robot, and this is our estimation, and this was done after 4 time steps. We got a very close estimation of the real estate. Unfortunately, not everything is happening with the Kalman filter. We know that there are some assumptions that really constrain the real world applications. On one side, the Kalman filter is very fast. As I said, they were able to use it in the spacecraft to go to the moon. So it is computationally fast. But now let me give you an example. If our robot is here and it moves here, we will expect it to be around here, right? But if there is an obstacle, the probability distribution that we have there might not be like a normal distribution, because we have to cut this part over here. We have to cut here. So we will start to study different types of distribution, multimodal distributions, and they don't fit with the Kalman filter. Additionally, the linearity is another problem, but for that there are some solutions that will be the extended Kalman filter. So on one side we have that the Gaussian functions don't adapt to many real scenarios, and we also have an assumption in linearity. Does not apply for all type of robots. Okay, so for the last bullet, we have something very good that is called the extended Kalman filter, which will remove the linearity assumptions, and it can also predict the state of the robot based on the assumption that everything is Gaussian. So for further reading, I really recommend the book Probabilistic Robotics from Sebastian Thrun. This is a great book. Like almost every roboticist have this book. and in this book you can find the whole analysis of the Kalman filter. We can have other methods like the extended Kalman filter, we can have probabilistic mapping, and this book is kind of the very important part in every roboticist. Finally, and something that we will study later, is the particle filter, which is also a base filter. Now we will remove the assumption that everything is normal. So that's all for today. Thank you very much, and see you in the next session.